Today we're going to be doing topic 3.2, part B. Basically, this PowerPoint covers the three gas laws and the ideal gas law. Today's objectives are the three gas laws, Charles, Boyle's, and Gay-Lussac's, and how do we combine those into either the combined gas law or the ideal gas law. And then we finish with understanding the kinetic theory of gases and when that model starts to break down. Okay, first off, there are three laws, okay? Boyle's, Charles, and Gay-Lussac's. In Boyle's law, temperature is held constant, pressure and volume will be changing. Charles's law, pressure is held constant, volume and temperature change. Gay-Lussac, volume is held constant, and pressure and temperature change. Okay, all of these laws are run under the assumption that the amount of gas in a container is going to be held constant. Okay. And there's a fourth law that says, which is Avogadro's law, which relates volume and the amount of gas. But we don't really cover that law. Okay, so pressure and volume first of all. Okay, this is Boyle's law that says if I have a container, okay, and I heat it up, okay, then as I have a container, and as I increase the volume of this container, the speed of the molecule doesn't change, okay? It's still pretty much because the temperature doesn't change, okay? But if I have a larger container, it hits the walls of my container less often, and therefore my pressure decreases. So as volume increases, pressure decreases. It turns out that pressure and volume are inversely proportional, or pressure is proportional to 1 over volume. Okay, if I look at a graph of pressure volume graph, okay, this is pretty much what the graph looks like for various temperature settings. Okay, on the left we have that hyperbola graph. P is proportional to 1 over V. So if I graph P and 1 over V, I end up with these linear graphs, okay, where the temperature represents the slope or how steep the graph is. So Gay-Lussac compares pressure and temperature, and it turns out that as the temperature increases, the kinetic energy or the velocity of the molecule increases until at some point it's going very fast. So if I keep the volume constant, okay, my pressure increases because my molecule impacts the walls more often. Okay, and so therefore as I increase temperature, pressure increases. So pressure and temperature are proportional. If I look at that graph, I basically have a graph that looks like this. Okay, volume and temperature in this case. As temperature gets cold enough, my gas is no longer a gas and it actually liquefies, so that's why I have that extrapolation there. Okay, but it's pretty much a straight line. In Charles's law, I compare volume and temperature. Okay, since temperature measures the kinetic energy, as the temperature increases, the kinetic energy increases in velocity. Okay. Greater velocity means that the impulse and the force against the sides is going to be greater. And if the sides are movable, I basically end up with a greater volume. In this case, it impacts the sides just as often, okay, but it has to travel more distance to get there. So it turns out that volume and temperature are going to be proportional. And the graph ends up looking like this, where volume and temperature, again, are going to be proportional. Notice again that the gas liquefies at different temperatures. At different pressures, it liquefies at a different temperature. But it's pretty much, again, this straight line that says volume and temperature are proportional. In general, we don't consider each law individually, but we work with either the ideal gas law, which is what I usually work with, or the combined gas law. The combined gas law basically says that pressure and volume over the temperature is a constant. It's going to be important in this case that temperature is in Kelvin. Okay, do not leave it in Celsius. This is the problem. This is where you will run into trouble. Okay, always remember that for the combined gas law and the ideal gas law, most of this slide, in fact, temperature must be in Kelvin. Okay, so in usage, what we do is we just use P1 V1 over T1, okay, pressure, volume, and temperature at some initial state is going to equal P2 V2 over T2 at some future state. Okay, it may be that in fact IB says we're only going to be changing two of these at a time. Okay, one of these variables, P, V, or T, will stay constant. So that leads us to the ideal gas law, which allows us to incorporate the number of moles of the gas as well. Okay, the ideal gas law is given as pressure times volume is equal to N, the number of moles, R, the gas constant, and T, the temperature in Kelvin. Okay, so PV equals nRT. I can change any one of those variables and figure out the change on another variable as long as I hold the other ones constant. Okay, which brings me to the four assumptions of the kinetic model for an ideal gas. Okay, the ideal gas law is the law that we use for an ideal gas, and that has four assumptions that we work with here. The first assumption is that gas particles are perfectly spherical. Okay, this is more true for the noble gases, okay, things like helium and radon and xenon, because they're monatomic. Once we get to diatomic or other types of gases, the spherical starts to break down, but they're still pretty close. Number two, all of our collisions, either against the side of the container or against other molecules, are going to be perfectly elastic. Again, this is actually a pretty good assumption because they don't lose energy, especially if they're in an insulated container. Number three, there are no intermolecular forces. Okay, this law is pretty good. Most of our gases are electrically neutral, which means they're neither positive nor negative. So there are no intermolecular forces. There's no bonds between them. And four, the volume of the gas particles is small compared to the volume of the container. There's a lot of space between the gas particles. Okay, so when does this break down? Okay, it breaks down in a number of ways. Okay, most of our real gases are polyatomic. Okay, oxygen, ammonia, nitrogen. So they're not spherical, but it's pretty close. Okay, our collisions are not perfectly elastic either. Some of the energy goes into exciting an electron or exciting the molecules of the container. And at some point, intermolecular forces will start to exist because I can liquefy a gas. Okay, as the molecules start moving slower and slower, they get next to each other and the intermolecular forces start to take over. So at very high temperatures, okay, the molecules become ionized and intermolecular forces again become significant. At very low temperatures, the average kinetic energy decreases and again intermolecular forces become significant. At very high pressures and very low pressures, okay, very low pressure is nearly a vacuum. There are not enough molecules in the container for our statistical significance. We do require that statistical significance because of the distributions of kinetic energies. And also at very high pressures, what I've basically done is I've made the container so small that the volume of the container versus the volume of the molecules is getting too close for the kinetic model theory to hold. Okay, so at very high pressures, the molecules are forced closer together, and again, my intermolecular forces start to become significant. Okay, thank you.